Welcome everyone to today's webinar in association with Optimove. My name is Niamh Gallagher, Head of Event Content at EGR, and today's webinar will be looking at identifying at-risk gambling behaviours using predictive modelling. So just some housekeeping. You can submit questions at any time in the chat box. We should have some time at the end for a Q&A at the end of the presentation. If not, after the webinar, we'll be sending a link to the presentation with details how to get in touch with our speakers. So I'll now hand you over to our speakers, Motti Coleman, Director of New Business, and Jonathan Inbar, Marketing Data Scientist at Optimove. So over to you guys.
Hi, good afternoon, everyone. Good evening, good night, those in Australia. I saw there's a few of you that's logged in from there, so thanks for joining at such a late time of the evening. As Niamh said there, we're going to be looking at some predictive modelling that Optimove's been building recently for our existing client base. The title, as you can see here, is trying to identify at-risk gambling behaviours using predictive modelling. So, I'm Motti Coleman. I'm the Director of New Business at Optimove. Sitting to the side of me is Jonathan Inbar. He's one of our lead marketing data scientists. Jonathan actually built all of the logic and the algorithms that sit behind kind of all of the presentation that we're about to talk about. So before I dive into the actual crux of things itself, just a little intro on who we are and why we're even able to talk about these kind of topics. So for those of you that don't know us, we work at Optimove. Optimove primarily is a customer retention platform. That's kind of been our bread and butter over the last 10 years or so, working with about 300 operators in the online gaming space, about 25% of EGR's Power 50, in fact, just a little bit over that. And that's given us the opportunity to see quite a vast amount of data from across the entire industry. Now, what we've done historically with all of our clients is we build out, effectively we're building out predictive models on top of customer behavior, and the application of those models were for the purpose of personalized campaign management. So the player value maximization through personalized campaign management. And obviously over the course, over the last number of years and more dramatically in the last year or so, obviously we've seen that there's a very deep look and a lot of owl eyes on the industry itself in terms of how we are regulating and how we're looking at the concept of problem gambling. It became very clear to us at Optimove that we have a big role, I think, to play in this field as well. And about a year ago or so, we started building out predictive models that were specifically targeted at the identification of at-risk customers in a very early stage of their journey. So everything we're going to be talking about with you today is actually about kind of lifting the hood up on the various different techniques that we use. Now, it's going to be a relatively technical topic because at a high level you've kind of heard everything there is to hear about it. So I think it's quite important that we actually show you some of, not all, but some of the techniques that we use that perhaps you can take away yourselves. And as Niamh said, you feel free to ask questions within the chat box itself or be in touch with us after the call. So I've spoken there already about the motivation for building a model, but social responsibility is probably the number one thing. So it's something that we should all be focusing on, all the operators should be focusing on at the moment. And I know that there's obviously a lot of focus on that at the moment. People are doing it from the perspective of email templates and the different types of marketing they can do. But of course, from a sort of self-exclusion or pre-self-exclusion perspective, that's the key motivations for building out this type of modeling. The other things we're going to look at over the course of the session. So we're first going to look at how we understand the data itself. We're then going to talk about selecting which particular variables. So what different pieces of customer behavior are we going to use in terms of understanding the types of model that we're going to do? How do we actually go about create and to analyze the model itself? And then finally, the application of the model. So what we're going to get out of the model, and then maybe a couple of sort of side points at the end is to just take it to a different angle. Okay, so we've already said the motivation for for building a model is that social responsibility. We're looking to identify at a very early stage the at-risk customers. Now, what we've done, and we'll see it in the next slide and going forward, we've taken a final point of self-exclusion, and the customers that self-exclude as being the ones who are defined as definitely at risk, or they're the ones that have created that risk, if you like. And what we're going to do is we're going to back engineer based on the concept of self-exclusion and try and have a look at the early identifiers in their customer journey. We're also going to look a little bit later on at the idea of there being obviously a very strong similarity amongst VIPs. So a lot of the behaviors that at-risk customers are displaying share a lot in common with some of the early identifiers of a VIP player as well. So how do you distinguish between the two? And through all of that, we're going to have hopefully an improved understanding of the customer behavior. Okay, so understanding the data itself. So I mentioned before that we're going to look at the concept of self-exclusion as being the end point of what we're looking at. We can actually see when we look across all the various different clients that we're working with, and this is what we've done. We've taken sort of a mass amount of data across multiple operators, and we can see that roughly 1% of the players are self-excluded. So we're going to be focusing on that 1%. Now, let's have a look at when those players become self-excluded. And we can see here from this analysis, if we look and actually wrap it around, we'll see that in the very early stage, in that first month, somewhere between 60 or 70% of the customers can become self-excluded. So we can think about the ideas of being able to treat different stages of self-exclusion differently. So you absolutely have a large amount of customers that are going to self-exclude much later on in their customer journey with you. You can see that there's obviously the over 1 year is still up towards the 10%. But the big majority of customers are happening over that first month. So that being the case, and we're going to focus quite primarily on those for the purpose of this talk, there's a lot of identifiers that have to be picked up fairly quickly. Okay, so we're going to look at some of those, again, those key behaviors that we're going to be picking up in an early basis. Now, we said before that it's only about 1% of the entire database of customers that are actually self-excluded. And that immediately creates a problem from a modeling perspective, because we're dealing with this concept of imbalanced data. What am I talking about there? Well, we're talking about the idea that our sample is obviously the ones that we're focusing on is a lot smaller than the entire data set itself. So you can see the ratio immediately. And that creates a problem, a very big problem in terms of the modeling itself. So we need to do something to the underlying data in order to start balancing it out. Now, from the way that this picture looks, and I'll explain it in a little bit more detail in a moment, it would look as though you were trying to balance it 50-50 in terms of the customers that we're focusing on, i.e. the self-exclusion versus the data set itself. You actually probably don't need that. You can probably do it about 10 to 15%. You can get it up to that point. But ultimately, what we're trying to do here is to take the two samples to be a lot more closer in size. Now, there's 3 different techniques for how you can do that. The first thing you can do is something called oversampling. Now, when we're talking about oversampling, effectively what we're doing there is we're duplicating the original data set. Okay, so we're taking the exact set of behaviors of customers that we've got, and we are repeating again and again and again that same set of behaviors until we grow that sample size to match the total data set. Okay, so that's the first way that we could start to balance out the data sets. The second thing we could do is undersampling. So we could take a random selection of the total data set itself and start shrinking it to get much closer to a final data set. And the final technique that we could look at is something called synthetic minority oversampling. Okay, now it looks similar to the first concept we looked at, which was oversampling. But what we're actually doing here by this concept of synthetic sampling is that we're taking the various different attributes, the various different sets of behaviors, and we're starting to plot new customers effectively that aren't exactly the same as the historical ones that we've got in there already. We're not replicating the same thing. What we're doing is we're finding very similar types of behavior and starting to fill out the gaps in between. So what a synthetic sample will actually do is potentially start creating more data points, more customers that have more extreme points, both at the low end and the high end of the sample. The oversampling is just going to, like I say, it's just going to fill out in exactly the same places of where it were. So a synthetic is going to provide probably closer to the reality of our expectation, but it could be a lot more. It could be a lot more extreme in the results that it produces. Oversampling is going to be maybe not necessarily the exact right type of predicted outcome in terms of the total data set, but it will be a lot more static, and therefore you can trust it a little bit more. Okay, so these are just some tools that we're going to use to handle the imbalance of data. Now, the next thing we're going to look at, phase 2, is the ability to select the variables. The first thing we should say is, what's a variable in of itself? And a variable effectively here is an attribute. So it's an underlying building block of player data, so a specific attribute. So how are we going to do that? The first thing we've got to do, if you look at the workflow, is the data loading. So that's just how we're going to get the data from you into Optimove. So that's not that interesting. The data preparation. So we're going to start looking at outliers and smoothing them off. Where it starts to get interesting there is at the bottom of data preparation. You'll see here feature engineering. And we're going to talk about feature engineering in a moment, but feature engineering is what leads us to the idea of variable selection. So it's taking our own insight into the data itself and starting to play around with some of the key attributes till we start to build out the relevant types of predictors. Okay, so that's what we're looking to do here, and we're going to go into that in a little bit more detail in a moment. So I'm just having a little bit of feedback. There we go, that should be better now. Okay, so after that, we're going to move on to the model factory itself, and we're going to talk about some of the algorithms, some of the machine learning algorithms that we use, and then finally how we deploy this. So through the idea of automation, the integration, the various bits of reporting that we're going to look at. So the idea of selecting variables. Now, why do we even need to select variables? The variables that you choose ultimately are the only ones that the algorithm knows itself. So you are going to predefine the best variables ahead of time. That's the idea of where the human touch comes into play. So specific data scientists, which is what we have sitting on our side working on things, they'll be looking at the various different attributes that exist, and they're going to be selecting the various different types of variables that they want. People often think that the best outcome of a model is created by the choice of the algorithm, but it's not. It's the choice of the different variables that you use and the various different combinations of those variables that you use. That's what boosts the performance of the model itself in terms of its accuracy, in terms of its precision. So you will have a data scientist sitting there potentially working with some automated algorithms that will help them choose the variables, and we'll talk about that in a moment. But it's very, very important that ahead of time you're choosing the right attributes, the right variables that we're going to embed into the model itself. You could also therefore be forgiven for thinking that you should just include all the various different attributes, all the various different variables in the model and just kind of get everything in there. The problem is when you have too many variables sitting over the top of a particular model, you start to get too much noise in the data itself, and your ability to tweak the model from the perspective of managing the various different combinations of attributes becomes problematic. So it's not just about throwing in all the various different variables into the model. It's about choosing the right ones and the right combinations of them. Now, in terms of how we choose the different variables, there's many different ways that we could do it. You can see here on this slide, I've labeled 1, 2, and 3, not cool, a little cooler, and a bit cooler than that. That was actually Jonathan that wrote that. So I work in sales, he works in data science. I think we probably have a slightly different definition of what's cool and what's not, but nonetheless, he has ranked these in terms of their coolness. And the first one he's looked at is the ability to manually test all variable set combinations. Now, very high level, what that would be doing would be to taking, if we've got 3 different attributes, test each, or 3 different variables, take each individual variable. So test variable 1 and see how it performs, test variable 2, then test variable 3, then test variable 1 and 2, then 2 and 3, and then 1 and 3. So it's testing all the different combinations yourself. Now that is plausible, and it can be obviously can be done, and it can be done in a 3 variable selection that I've just explained. The problem is when you start growing the number of variables that you're going to use within the model, the ability to test this on a manual basis becomes exponentially harder, which is why Jonathan thinks it's not that cool. The next thing that you can look at is the concept of bivariate metrics. Okay, so it's similar here in terms of the correlations, but where bivariate metrics tends to be a little bit more relevant when it looks at the connection between 2 individual attributes is when you're dealing with the idea of a linear metric. So a linear metric would be something like saying the more that a player deposits, the more you expect the deposit amount to be. Something like that might have a linear correlation. But most attributes and most things that happen in the world don't follow a linear path. So something like the deposit amount to the win amount is not necessarily linear. Now, you might have many variables that are non-linear. In fact, most of your variables will be non-linear. And in as such, bivariate metric testing would probably be not the best use. The third thing you can do is to loop through all the variable set combinations. Effectively, what that's doing is taking the manual testing and it's putting it into an automated process. The automated process will start ranking the various different combinations of variables against each other. The best ones, it will rank high enough to the point where you're selecting those ones to go within the tool. Now, what we do, we go one step further than that. We use something called an automated variable selection algorithm. That is a tree-based algorithm. That's one of the things I've been told I'm not allowed to talk about in terms of too much detail. That's, I suppose, Optimove's secret sauce. Some of that IP will remain as Optimove's IP, but Jonathan tells me it's super cool, so I'm gonna trust him on that. But again, these are just some of the various different ways that you could go about selecting your variables. Now, when we're talking about taking those variables and actually selecting them, we're going to have two major challenges. The first one is how do we transform raw gambling data into relevant behavioral variables? We'll talk about that a little bit more in a moment. And then how do you address over-identifying variables? So we're going to think a little bit outside the box here. Now, regular betting behavior attributes will be things like your bet amount in the last 7 days, or your deposit amount in the last 7 days, or today. They're kind of very one-trick ponies. They're very at the point of reckoning a specific attribute, and they're not great for determining behavior. The reason they're not great for determining behavior is basically because there's no relativity involved in it. There's no trend that's connected to it. So particularly when you're talking about the idea of problem gambling, one of the key concepts here is to see how player behavior has changed over time. So a single attribute doesn't really tell us that. What we need to do is transfer those individual betting attributes and turn into something more interesting. Things like change in bets over the last 7 days, change in deposits over the last 7 days, ratios. So all of that kind of stuff starts to be a lot more interesting. So we start to generate a single attribute from the multiple attributes there that we're building. So you can see here we've got a daily bet amount over 7 particular days. Now you can see with your own eyes, obviously, that there's an upwards trend that's being created as a result of the betting behavior change. What we need to do is to turn that trend itself into a single attribute. Now that leads us down the path, I don't know if sort of GCSE or high school maths, but go back to mine, thinking about things like gradients and stuff like that. So basically we're looking at the slope, we're looking at the steepness of the slope, i.e. how that trend is changing, affecting your change over a period of time. So that's what you're going to do. You're going to measure the trend line slope rather than taking 7 individual days of betting behavior. So you're going to get one single attribute. And we're going to start using those as a way of putting variables into the model. The next thing we're going to talk about is the idea of an over-identifying variable. I'm going to do something you're not supposed to do in presentations, but I'm going to read directly out from the slide to you because I've built here an example of exactly what it should be, and it should really identify here exactly what I'm referring to. So we've got a common example here of the idea of rare countries. Okay, all players based in Serbia are almost certain to be self-excluded because there is only one player based in Serbia in our data set, and he is self-excluded. Okay, so the machine learning makes conclusions because it has a tiny data set, and this would be an example, like a rare country. So what we need to do, we need to obviously avoid that. We need to avoid the machine learning making very extreme decisions, very extreme analysis, because the data set is very small and the results are all tending on one particular side. The way that we're able to avoid that would be to group the rare countries all together as one thing. So for here, we might say a high level category, the majority of players from the UK, then you create two categories, UK and non-UK, rather than multiple categories where you might have a small number, a small data set in each individual variable. Okay, so we're looking to transform our raw data into something that becomes a lot more useful within the model itself. Okay, we're going to look now at just the type of model. I'm not going to really talk too much about that, but the model itself is a binary classification. So you've got many different types of models, but a binary classification is one that we're looking at here for the idea of, is a player at risk? And the answer is yes or no. Okay, so that's a binary classification. The other would be, predicting what future value would be, or predicting what churn rate would be, which is something that's a lot more linear. But again, the idea, if you took the idea of churn, is a player going to churn or are they not? So again, back to the point of binary. So when you're talking about a binary classification, the different types of models that you could be using, just some examples here. Again, I'm not going to go into them, but it's just for you to take away. And if you wanted to look into more detail, you can. So something like a logistic regression, a random forest, or gradient boosting. These would be the sort of models that you might attempt to use yourself. Now, the next thing we're going to look at, and this is kind of the crux really of all of this, is the ability to analyze the model. And actually, this matrix in front of you, this is called a confusion matrix, and I think it's a pretty well titled matrix because it's pretty confusing. So I've tried to break it down. I've tried to unpack it all in my own mind a little bit. I'll try and do the same for you now. What you can see down the left hand side is our prediction. So we predict a customer. In this particular box here, we're seeing all the customers that we predicted as being not self-excluded. And then across the top, you can see the real outcome. So they really were a no self-excluded player, or they really were a yes self-excluded player. So if we just look at each individual box there, this box would be the players that we predicted as not being self-excluded, and it turned out that they weren't self-excluded. These would be the players that we predicted were not going to be self-excluded and were and actually turned out to be self-excluded. And then the inverse again is obviously going to be the case here. These are the players that we predicted would be self-excluded and turned out not to be. And these are the players that we correctly predicted would be self-excluded and then turned out to be. So what we're doing here after we've built a model, obviously when we're building a model, we're using all of our historical data. We build the model, we can go back to all of the historical data and actually check, kind of go back in time a year, insert our model into the player behavior in time sort of -1 year, and then see what happens. So that's exactly what this matrix is telling us here. Now, when we do that, we're going to get 3 different types of analysis that tends to be used in kind of looking at the performance of a model, 3 different KPIs. Those 3 are accuracy, precision, and recall. Now, accuracy is fairly, actually, let's just strip it back a second before I even do that. So I just want to talk about some errors. Okay, so if you can see here the idea of predicting no, okay, so we've predicted that players are not going to become self-excluded, and it turns out that they were self-excluded. This up here, for the sort of data people amongst you, this is called our beta error, and this here is our alpha error, whereby we're saying we predicted that customers are going to become self-excluded and they turned out not to be. Okay, that's a problem for us. The ones that we got wrong are a problem for us. That's why they're called errors. The question is, how much of a problem are they for us? Now, the whole idea of why we're building this model is we're trying to predict who our self-excluded customers are so that we can make sure that we do something about it at an early stage. That's obviously going to be the output of the model. Can we prevent players from eventually having to become self-excluded and identify that at-risk behavior early on? The problem is here with these 767 customers, we've actually missed them. We predicted that they weren't going to become self-excluded, and in fact they did. They slipped through the net. So for the purpose of this type of modeling, actually the error that we're looking to reduce is the beta error. We're trying to make sure that not too many customers slip through the net. Now, if we're able to do that, what we would, the way that we would tweak the model to affect that. So let's say we used something like the growth in deposit amount as one of our key variables. If we were to drop the threshold of deposit amount growth, what we would do is we would capture a lot more of these players. We would drop that. But if we drop that, we're going to increase that. We're going to predict that a lot more players are indeed self-exclude and make more of a mistake and say that they're not. Now, again, for the purpose of trying to predict self-excluded players, we might be okay with that because we're more concerned about actually not identifying these players properly than making the other type of mistake. If we flip that logic on its head, if we're talking about the idea of, let's say we were trying to predict VIPs, we actually might not be too concerned with not predicting a VIP correctly. We might be concerned with over predicting VIPs, because what we do with our VIPs at an early stage is we give them massively high bonuses, and actually what we want to make sure we don't do is give away too many bonuses. So depending on the type of modeling you're doing and the outcome that you're looking to achieve will depend on how sensitive you allow the model to be and which particular area you look to tweak. So again, let's go back to the KPIs of the modeling itself. When you deal with the idea of accuracy, that is pure accuracy. Did you make a correct prediction? So you'll see here, that's our prediction of no, and really no. Okay, so you were correct there. You predicted that they were a no, and they really weren't self-exclude. Or alternatively, you predicted that they were yes, and they were indeed yes. Okay, so these we've predicted correctly. So your model is accurate to 95%. Actually, that's probably not that interesting in this particular type of modeling, because any random selection of players that were no, we already know that 99% of players don't self-exclude. So when you've got such a sort of a shift towards that, you would always expect that, you know, even at a random testing, the prediction of no would be pretty high, right? So that might not be so helpful here. The next thing that we can look at is the precision. So this is the idea of looking forwards. If you were predicting, and this is, you know, obviously very key to what we're looking at here, if you're predicting that a player is going to be self-exclude, how many of them really did self-exclude? So you can see here that 82% of the customers that we predicted to be self-exclude customers did eventually become that. So precision is a forward-looking analysis. The final thing that we're going to look at is recall, and recall or sensitivity, that's a backwards looking, okay? So out of all of the eventual self-exclude players, how many did we miss or predict correctly? And the reason that I talk about it from the idea of sensitivity, because this in this particular model is going to be what we're going to be looking to tweak. So we wanted to drop that 767 and increase the 4716, and we already understood we're going to do that at the expense of the other type of errors. Now, just to get an idea of how good the model is, so we would use probably precision, and we would say, is our model performance good? If, in this particular example here, a monkey or a chimpanzee probably was to predict randomly if they could pick out a player that's going to be self-excluded, would they be able to? And we already know from the underlying data itself, only 1 in 100 players are self-excluded. So the precision here of that particular model, albeit an example, was 82%. So obviously you're looking at a massive, massive uplift between your ability to manually or just to guess versus what the model can actually achieve. Finally, we're going to look at some of the applications of the model. Okay, so the model itself is effectively going to produce, you know, a set of answers, and what you can do with that is either build a new attribute of customer, so a likelihood of a customer becoming self-exclude. Maybe you're going to rank that or just give it as a percentage, so that could be as an attribute itself. You could produce a daily list that gives you a sort of a threshold, a list of customers that at the moment are at certain levels of risk based on all of those behaviors. The early identification, you might start limiting the amount they deposit or trying to drop that, you know, the deposit growth over a period of time. You might start to drop it off before you finally exclude them on, you know, kind of for their own good. And of course, we can do periodic reporting. I suppose the last thing that I kind of want to touch upon, and it was something that we brought up right at the beginning, was looking at the idea of a VIP versus a problem gambler. Now we all know the VIP paradox, the Pareto, which is of course that a small percentage of your customer base produces a massive contribution to the overall revenue picture. So your VIPs probably sit somewhere there at the sort of 90 whatever percentile, but are producing, like I say, a huge part of the total revenue contribution. If we were to focus just on that final piece again, you would, if you zoomed in, if you magnified the glass a little bit more, you would see the same kind of concept going again. And of course, sitting in there somewhere are going to be at-risk players, as we've seen across the entire data set, but there are also going to be at-risk players that are sitting there within our VIP section. Now, the big problem that you've got, and I suppose it's magnified more when looking at VIP, is that your at-risk player obviously has some kind of gambling problem, but because they meet the VIP definition, we're going to apply into this customer huge deposit and bonuses, huge VIP bonuses, and all the sorts, maybe some kind of VIP hospitality, all that kind of stuff. And in doing so, of course, we're just fueling the fire, and the situation is getting much worse. And that, again, obviously, that's the same concept for any of our customers, but it's particularly magnified when talking about our VIPs. Another reason for that is when we've gone and actually looked at the populations themselves, again, going back to the data across all the various different clients we look at, we can actually see that there are 6 times as many self-exclude customers within our VIP segments, if you like, than in the regular population. So there's a 6 times chance of our VIPs being at risk. Now, that being the case, and there being such a wide variance between the behavior of VIPs versus the behavior of non-VIPs, what we would actually recommend to do is to separate out the VIPs from the non-VIPs and probably run a model separate to each of those, and go again back to all of those kind of synthetic techniques to boost out the number of players that sit within there. So that completes the talk for today. Obviously, we're going to have a little bit of time now for questions. So we're going to look at some of the questions that we've got on there. Okay. So let me just go. I'm just looking at them now for the first time. Okay. So and I'm going to hand over to Jonathan, but I'll read out the question here. 1% for self-exclusion seems fairly low. How did you distinguish players who self-excluded because of an issue compared to players who self-excluded because it was easier than closing an account?
Okay, so that's a good question, and I want to refer to also something else I saw in another question about like the other like how reliable it is to use the self-exclude as like our anchor. So basically, when we're starting the process with our clients, we sit and we think together what will be the best thing to start with, or to start with, like maybe a basic model to work with. We found out that like all those kinds of status data, like self-exclude and account being closed and things like that, are not like something that is that easy to bring to us, at least on like a daily log form or something like that. So basically, just to start, we basically agreed that we can start with self-exclude because it's a good anchor point to work with, and then we can maybe make the model more complex and add like other statuses when we see that this one really brings value. And in terms of like distinguishing between the types of self-exclusion, so this is like up to the client to give us the correct player, basically. So we've asked to specifically get the status of players who self-exclude because of an issue, so we can only enter this into the model. So it's basically up to the data that the clients can give us.
And that kind of leads on from what Jonathan was saying there to another question, which I'll take as well. It's the first question that came up. It said there's a contradiction between player value maximization and responsible gambling. How do you or your clients look at that tension? Who uses this so far? Can we speak to them? So, I mean, the first part of that question is I suppose the crux of everything that we're trying to do here. And there's a very thin line, I suppose, and that's the responsibility on all of us, the contradiction between player value maximization and responsible gambling. And again, it depends on a per operator basis. If we think back to, and I'll just go back a few slides, ultimately that's what this particular analysis of the model really helps us do. Each operator is going to have their own determination for the answer to your question, because as I said, if you're looking to take out 100% of these customers, which is not achievable, of course, but tending towards 100%, if you do that, if you try and reduce the number of players that you miss, i.e. identify all of the players that do eventually become self-exclude, what you're going to do is set the parameters so low that you're going to end up including a huge number of the players that actually weren't self-exclude. So in doing so, the ultimate result of that is on the bottom line. The ultimate result of that is going to be on the value maximization of other players that were not actually at risk, but you've now included into that because of how sensitive you've been to the idea of trying to predict self-exclusion. Now, we, as I suppose the third party, is the tech companies, the data science and modeling team that sit aside that, we won't necessarily advise what you should be determining, what you should be looking for. We'll be the ones that are going to affect the change, right? So you will come to us and you're going to tell us. And by the way, that's why all of our modeling is completely bespoke for every client that we work with, because they each have very different they have different needs and different requirements. Some of them will be a lot more sensitive to the issue. Some of them will be less sensitive to the issue. But you're right, it will have for sure an impact on value maximization. In terms of who've done this so far, well, the only one that I would talk about, simply because they did a massive press release about it in Italy. So Sisal, who we work with in Italy, have been obviously very, very heavily into this with us for a long time. Like I said, they did a massive press release about it in Italy maybe 6 months ago or so. So they would be the ones that I'd point towards. And if any of you can read Italian, which I cannot, or rather understand it, then there's a lot of Italian press surrounding it. Yeah. The next question we're going to look at, we've probably got time for one or two more, is the question is, how frequently do you retrain the model?
Yeah. So I'm going to take this one. Basically, this, and also like I've seen a lot more questions about like using the self-exclude as our anchor here, and I want to say it's really a teamwork between our team and our clients, and we define together if we want to use this, and we obviously can use other criteria to define the target variable on the model, right? It doesn't have to be just self-excluded, but it's what we've discussed with our clients and chose together. And in terms of the frequency of retraining the model, so we try to make a model that will be robust and last for a really good time. So what we can automate, we do. And usually, with the relationship that we have with our clients, we do a review of the model results every couple of months, and then tweak it or retrain it again to basically improve the results, or if we need to change it completely, then we just do that.
Okay, I'm gonna summarize. I mean, I'm just looking at all the questions now, and there's a huge number of questions, and obviously not going to be able to deal with it, all of them, although I'd really quite like to via email after this. But a huge number of the questions, and by the way, it's the same question I asked myself when I first when we first broached the topic, was the idea of using self-exclusion as the anchor, right? And it was the kind of the first thing that I said to Jonathan when we were looking at it. And the answer is that, I suppose the question is, there are many other players that are at risk that are not self-excluded, and you're right. Everybody in saying so is right. I think one of the issues that the industry is facing at large is that there's no, and it's something that we're looking to speak to the regulators about ourselves, and we'd be very interested to hear feedback from all of you, from the operators. But there doesn't seem to be one clear definition of what is an at-risk player, or at what point problem gambling actually takes place. So given that there's no centralized agreement on a benchmark for it, we have to use other anchors in place upon which to build the predictive model. For the purpose of this particular discussion, i.e. the one that we are all having together right now, we thought that would be a very good place to start, which would be to look back at self-exclusion and say it's very likely that our self-excluded players are problem gamblers. But that doesn't mean that they all are. And it also doesn't mean that we've captured the full scale of different players that exist. And that's what we would do with our clients. We would have a discussion. We would have a discussion with each and every single one of them, and we would look for the various different anchors in place between that they believe defines that their own set of players. But again, this is something that we're looking to really get feedback from other people as well. It's something that we take a lot of interest in. It's something that we're looking to discuss with the regulators themselves. And I really appreciate any more feedback. So we had something like 30 or 40 questions in there, and sadly, we don't have any time to answer any more of them, but we will really look to try and get back to you post this meeting. All of those questions are actually anonymous. So if you asked a question and it wasn't answered, and if you have any other questions that you didn't ask and you'd like to, I believe that EGR will be sharing our contact details. Feel free to be in touch with us about that. We'll also, of course, be at ICE in the next couple of weeks. And be very, very happy to talk to any of you in person about the concept. We'll have a bunch of our data scientists there as well that have built the models for our additional clients. So thank you very much, everybody, for your time today. It was really interesting from my side to research this and to talk about it, and I look forward to having more conversations with you all in the future.
Okay, thanks, Muddy. So as you mentioned, we're just about out of time. So if anyone does have any follow-up questions, we will be sending the link to the presentations with details to get in touch. So thanks again to Mossy and Jonathan and Optimove. Thanks all of you for joining in. So have a good day. Goodbye.